going to be the last class, and I told you guys you get to decide how we do the class. Either I teach you one more thing and ask questions on it on the exam, or you keep me entertained by asking interesting questions. Either which way is fine. I am prepared for both. I have a lecture, a mini lecture on first order logic. I also have a couple of things, and I do want to spend like the last 15 minutes or so, doing a quick review of the topics that we have done. This is not meant for recitation for the final exam. You know, that you still have to do it separately. As I said, the final would be take home, okay, and I will try to get you more details as it's that the take home would be due back on Tuesday, which is the final exam day. Okay, so I will give it to you before. I will try to give it to you by Monday or earlier than Monday, depending on when I get to set the exam. Okay. As I said, the topics would be more towards what has been done. I mean, this is a take-home, so there is not too much surprise. You know, after you look at it, you can see what the topics are. But I will I'll ask you more questions on the stuff that we have not had in the test until now. But there will be some comprehensive questions. Okay? Yes?
Do we just turn in a hard copy to your
Yes, you do have to give it in a hard copy, because otherwise I will have to print it. You know, I mean, there is any, you know, I can always make small exceptions for, you know, really relevant cases, like I'm already on the top of Mount Everest, I can't come back and give it to you, I'll print it for you. You know, but generally if you're around, it's better you give me the hard copy. Okay, so any other questions regarding the exam? So this is the final homework is due here. I'm going to post the solutions on this too. As to, I guess, the grading on the homework, when it gets done, I'll let you know, but it may well get done only next week. Okay? But the solutions would be posted for you. Okay? Any questions on the test or anything? And more mundane questions. You're going to ask all these neat questions in a minute or two, but I mean, what happened to the printer paper is not a good question to ask, because I can't answer it. Apparently it's out of it. Okay, so there, this is my, I think I invented this the other time. I don't know that, are they still showing the Visa commercial on the TV? It's not particularly topical anymore, because they used to show this Visa commercial where they'll show a whole bunch of things, and then the last part is supposed to be, I guess, what is the cost of spending all your life, these 4 months, I guess, presumably part of it at least. And I'm hoping it's priceless, because I didn't get much of a money. And then one other thing for a few of you who might know this, what is Stockholm Syndrome? And what's the connection between that and this class? Okay, try to think about it. Does anybody know what Stockholm Syndrome? Yeah?
It's when, isn't it when someone grows an attachment to their captors?
Exactly. Exactly. So to the extent, I'm hoping for Stockholm Syndrome in this class, that you know, you learn to like the pain, and that you hopefully gotten used to the course. Okay. So that's the one. You know, that's just the connection there. So before I go forward, so are there questions? As I said, there are 2 different ways we can do the class today. One is you ask me, I mean, we can basically, I think around, what's that, 5:30? Around 5:30, just before 5:30, I shift into the review part, and that's about 15 minutes of review. But before that, we have, you know, time. You can ask me questions. I can also suggest a game where you connect things on the board. And if neither of them are going well, I will teach you first order logic. right? I mean, so if you keep quiet, I would understand that you love my teaching and you want more teaching of more topics, in the few minutes that are left in the course. Anyway, so are there questions? Anything that anybody wanted to get off their chest across the course about connections, about things that were missing, about something else that you thought might be done in the course and wasn't done? I mean, this is not all surprising, right? I did send a mail saying this is how this class would be. So,
I didn't understand the concept of pattern databases.
pattern databases. Okay, so pattern databases, essentially all it is saying is that the more important thing to understand there is instead of, so if you consider the 8 puzzle problem, let's say, that's a good place to start from, you can remember the shortest path from every possible 8 puzzle state to the goal state. Okay, and if you remember that, then you have the perfect heuristic stored away, and then you don't need to do anything after that. The search becomes very easy. Okay, but that would be an extremely large database. Okay, another option would be to essentially, if you have an 8 puzzle, then to get to the final state, you need to get this part of the final state. So in the sense, to make a picture of me, you need to make a picture of this part of me. I'm not saying anything particularly surprising here. To make the complete picture of me, you have to make the left side of me also as a picture. Okay? So if you are going to get to a final configuration, then on the way to it, at some point of time, you have to get to this configuration correct. So then you can, instead of remembering the distances from any arbitrary state to goal state, you can remember the distance of, given any arbitrary configuration, how much time would it take for me to just get this part correct? How many moves would it need to just get this part correct? So for example, in the final configuration, you may have this 1, 2, 3, 4, 5, I guess, let's say. Okay, so all you need is get wherever 1, 2, 3, 4, 5 are here, have to be in the correct configuration. The rest of them, you don't care where they are. So you may as well act as if the rest of those tiles don't have names. Only 1, 2, 3, 4, 5 have names. The rest of them are just seat warmers. Okay? You can't walk over them. You still have to move them, but you don't really care where they will wind up. If you do that, you essentially have gotten a pattern database which gets this pattern. And this database would be smaller than the perfect heuristic database and be cheaper to compute. The bigger the pattern, the more effective the database is.
So are we using it somewhere, pattern databases?
We did no. I mentioned that as a way of getting more effective heuristics. Pattern databases are used a lot. I didn't talk about this in the course, other than I think I gave an extra credit portion. I don't know if that anybody actually did it. But you can also, for example, think of the same sort of idea, although it's not pattern databases. In the planning graph, if you just do positive interactions, you get one heuristic. You do positive interactions plus binary mutexes, you get a better heuristic. You can do positive interactions, binary mutexes, and ternary mutexes. You'll get even higher, even better mutex. So again, you are improving the quality of the heuristic by doing more and more analysis upfront. So pattern database gives you a sliding scale way of increasing the accuracy of the heuristic. Other questions? Yeah? So I'm told once in a while that students really like discussion courses. So as long as other people discuss, I think they like it. It's like, we don't want to discuss, as long as somebody else is discussing, we can tune off. Yes?
I was just a bit hazy in the actual implementation of the perceptron in the homework assignment. When we actually had to implement, we were given the rate like I understood the concept of it, but when I was actually trying to apply it, I'm not sure if I did it quite right. And I was wondering if we can kind of like go a little bit over more about how you would like change the weights given alpha, because I wasn't.
Yeah, I mean, I think all we were saying in the perceptron scenario is if so clearly you know the. So the important thing in perceptron case is the error, right? So you have you know, a unit, and then it has a bunch of inputs, including the threshold input. Okay, that is W0, W1, blah blah blah, to WK. So there are K input things, and then there is an output here, and so you have a particular training example. That training example basically told you what the weights are. I'm sorry, what the initial state is. So in the training example, you said I1, etc. up to IK, and imagine there are like some, you know, for now just assume they are a Boolean. So this 1, 0, 0, 1, etc. So you clamp them here. Remember, this will always be clamped to -1 because this is a threshold, so it's always clamped to -1. So then what happens inside of this is it sums Wi times II, right? W0 times -1 plus W1 times I1 plus W2 times I2, etc. And then it sums this and it checks to see if that sum is greater than 0. Right? And if it is greater than 0, it puts a 1 outside. If not, it puts a 0 outside. Okay, right? Now, if I gave you a training example, this is the training example. I also told you its class. Okay, so the class for this, I would have said, let's say it's a binary classification problem. I would have said maybe it's an example of the concept, or it's not an example of the concept. If it is an example of the concept, I would have put a 1 here. Now, if you started the perceptron by initializing the weights with something, right? And then you threw in these inputs. And if it will say something outside. If it wound up saying 1, then the error between what it should do and what it did do is 0. So nothing needs to be changed as far as this example is concerned. Right? Whereas if it had said 0, then it has an error. Right? And how much is the error? The true value is 1, and the value it gives is 0. So the error is 1. Okay? And so there is a positive error. So basically, if you think about this, it's making it 0. That means the sum is becoming less than 1. I'm sorry, less than 0. Okay, so remember this is a threshold unit. Okay, if the sum of all these weights times their inputs, if it is greater than 0, then you will get a 1 here. If it is less than 0, you will get a 0 here. It gave a 0. That means the sum was less than 0. But you need the sum to be increased so that you will get a 1. Because in this particular example, you need to get a 1. To do that, you need to change the weights. Right? So for example, suppose this guy's input is -1. Now, is this weight supposed to increase or reduce? Remember, the total sum needs to increase so that you will get a 1 outside. Right? I mean, probably this guy came as -0.5. That's why, when you thresholded it, you got a 0 here. So all these guys should change themselves such that for this example, it won't be -0.5. It will be like +0.1, let's say. Then it will become 1. You'll get the right answer. Okay, so all these weights are trying to push this sum higher. Okay, if this is -1, what should the weight do so that the sum will become higher? If I increase the weight, the sum will become lower. Right? Okay, so I will reduce this weight in this case. I have to reduce the weight. So I have to reduce it how much? I'll basically reduce it by W1 is set to W1 minus alpha. That's what you're doing in the perceptron. And in a more correct thing to do would be, instead of taking a constant alpha, you would essentially be actually considering the gradient of the error function at that point, and then use that to decide the step size. But perceptrons will also work for just constant alpha. They just probably oscillate a little more. Okay. Yes, sir.
Any question about this example still? I believe in the homework we initialized all the weights to 1. How do you decide what you should actually initialize all the weights?
It doesn't matter. Doesn't matter. Because what happens is, as I said, in fact, I think I hope I asked, that you can, if it's a, if it's a two-dimensional features, I mean, if it's a two-feature examples, then you can easily see that, the perceptron equation will correspond to a line. If you put random down weights, then it corresponds to a particular line above which should be, pluses and below which should be minuses or whatever. I mean, as long as all pluses are on one side, all minuses are on the other side, you are fine. Okay, as you keep changing the weights, this line keeps changing. Okay, so it doesn't really matter where you started the line with, because once you start feeding in the examples, you're looking at the error and seeing how to modify the weights. Okay, one interesting point that I didn't mention last time, since we are talking so much about perceptrons, I might as well mention here, is in fact, so suppose I have plus here, minus here, okay, right? Now, it turns out that any line, I'm sorry, not even color line. Any line all these lines separate pluses from minuses. Do you see what I'm saying? So perceptron doesn't have a unique solution. It basically will converge to any set of weights that will correspond to one of these lines. Actually, there are how many lines? There could be infinite number of lines. Now that you can actually get a line, the question would be, are all these lines really equally good? And one might say that, in fact, I would say probably that this line, and consider this other line. Okay, which one is better? Is this better, this better, this better? When they're all separating pluses and minuses, which is better? Do you have an intuition?
Blue.
The blue, because
Farthest from.
it's basically kind of trying to be equidistant from the pluses and minuses. In particular, if you consider the distance of it to the closest plus and the distance of it to the closest minus, it's making sure that it's almost as if, so remember these points, these are points in high dimensional space. Points also can be called vectors. So you have two vectors, these are all vectors, these are all vectors. These are the positive vectors, these are the negative vectors. Any line that separates positives from negatives is a perceptron. But one interesting thing is that you might want to say that which of the lines are likely to be more robust. If you learn more examples, you are likely to find, for example, that one more negative comes right here. In which case, this guy is no longer the perceptron. So not only do you want to learn based on what I told you, but you also want to learn such that you don't have to relearn right away tomorrow if Chitta Baral tells you something a little more. Do you see what I'm saying? Okay, so in some sense, the right thing to do, the conservative learning to do here would be to, in this particular case, to see that these two vectors, these are the closest plus and the closest minus. The line should somehow be sort of equidistant from them. So you can think of these vectors supporting this line with these little perpendiculars. And this would actually get a better line separation. And this idea is called support vector machine. right? Things are just all close by. You must have heard of support vector machine. This idea is called support vector machine. Okay? And essentially a support vector machine finds a perceptron that is sort of the most conservative perceptron. That's not likely to change if you see one more example. Eventually you may have to change it, but it's just that, you are being very conservative. You are being away from, equally away from both the positives and negatives. That's the support vector machines. Okay, and one more thing I was going to mention last time actually when we came here is having understood the support vector machine. So for example, in the case of support vector machines, it turns out that this is an actual optimization problem. You need to find the line such that it is equidistant from the closest plus and minus. And it turns out, there is quadratic programming. It becomes a quadratic programming problem, and it can be solved easily. Okay, it's not as easy. The inference is not just the way support vector. The perceptrons you just get to keep changing the weights until it stabilizes. Here you just solve the, a quadratic program to get the best line directly. Okay. Now another interesting point, since we talked about support vector machines, is suppose it turns out that I do not have linearly separable data. Remember, the perceptrons as well as support vector machines try to draw a line between the points. What if I have something like this? Something like this, where I have a nice big circle. Everything inside the circle is plus. Everything outside is minus. That's how the concept is. Can you learn a perceptron? No. Can you learn a support vector machine? No. In fact, you should know that if you can't learn a perceptron, you can't learn a support vector machine. Because support vector machine is the best perceptron. There are no perceptrons to begin with. There is no best of them. Right? Now, one of the interesting things is, while this is not linearly separable here. So here you have x-axis and y-axis. Okay. It turns out, I hope I remember the picture. I can't draw the picture as well, but if you were to, instead of taking x and y, if you were to take, so you have one dimension x, one dimension y. I suggest you consider these three dimensions, x squared, y squared, root xy. I'm increasing the dimensionality of the problem. Right? I'm increasing the features. I told you that many features are sometimes irrelevant, you want to get rid of them. But here I'm increasing the features. If I were to do this, then I essentially now have a three-dimensional space. One axis is x squared, one axis is y squared, one axis is root xy. If I were to draw each point here, which has two coordinates, has three coordinates in that space, right? If you were to put these points in that three-dimensional space, turns out then what you need to have in three-dimensional space is a plane separating pluses from minuses. It turns out that in fact the plane would be there. So while the data is not linearly separable in the lower dimension space, it becomes linearly separable in the higher dimensional space. Now if you are surprised at this, you shouldn't be. If I have 300 data points, okay, tell me a dimensionality of the space where I will certainly be sure that there will be a plane that separates pluses from minuses. 300 dimensional space. Because then everybody is unique. So everybody has their own dimension. So each data point becomes a dimension. So D1 will become a dimension and it will only have one, only the first data point will have one in that dimension. Everybody else will have 0. D2 will only have one in the D2 dimension and will have 0 everywhere else. If you go up to there, I understand we don't have a very good, intuition about higher dimensions. But if you go up to there, you can, if you think about it, you can see that it's clear that anything can be separated at that level. The question is, can you separate it before? In this case, the number of points here is probably like, if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I'm saying 16-dimensional space, this would be linearly separable. But I showed you a 3-dimensional space where it's also linearly separable. So the trick would be to find the 3-dimensional space, like a small dimensional space which is higher than the current dimensions, where the data becomes linearly separable. That means there's a plane separating them. Separate them there. Find the equation of the plane in that place. If I were to find the equation of the plane in that 3 dimensions, I can come back and find its equation here, because I know how to transfer the coordinates back. Right? It will correspond to some kind of arbitrary curve. So I said that you normally need neural networks of multiple layers to get nonlinear surfaces. But here is another way of getting nonlinear surfaces. Basically blow up the dimensionality, find a line surface in that higher dimensions, and then come back and then basically convert, not line, the plane, hyperplane, and convert that hyperplane's equation back to the lower dimensions. If you do this, then you have another way of dealing with, finding a line nonlinear separation dimension, nonlinear surfaces that separate pluses from minuses. Now this doesn't look like a particularly computationally efficient idea, because I'm saying consider every possible way of blowing up the dimensions, try if there is a plane there, if so come back. Okay? But it turns out that there's some nice theory that which basically tells you that if you essentially were to decide there's this idea called kernel trick. I won't talk to you about it here, but what the kernel trick allows you to do is in one fell swoop, takes the data to higher dimensions, finds the plane that separates them there, and converts it back to lower dimensions. And so then you have this idea called kernel machines. Kernel machines essentially are taking data from lower dimensions to higher dimensions, separating them there, bringing it down. Which higher dimensions are they taking? They won't tell you. Okay? But the intuition behind the idea comes from this. Essentially, you are in one fell swoop going up higher dimensions and coming down. Okay, that's kernel machines. Take machine learning course, we'll learn something about that. Yes?
So I was reading about this, the other learning algorithm, logistic regression.
Mm-hmm.
So it seems to be very similar to perceptron. So what are the relations?
Logistic regression is regression. So the difference between logistic regression, so there are the two kinds of learning techniques. One is classification, which tries to map every input vector into 1 or a 0, or certain number of discrete classes. Okay? A regression, on the other hand, maps an input vector into a real number. So perceptrons applied to regression problem is close to logistic regression. Okay? A regression problem basically means, basically given, variety of attributes of a student, tell me what their grade would be. That is a classification problem, because they only have, discrete number of grades. Given the attributes of the student, tell me what their height would be. That's a regression problem, because height can be a real value number. Okay?
In this perceptron learning, we do the weight adjustment, like when we are going to stop the weight adjustment?
When the line doesn't change. When basically you have no more errors, essentially. Because then remember, any of those infinite lines, if you get one of them, you would find that they have no error anymore on the pluses or minuses. And if the error is 0, then you won't change them. That's the interesting part, because if you remember that previous picture, this line as well as that line, they both will give you 0 error. And so you think they are both equally good. Okay, something other than perceptrons now. Okay, one thing that I can try and see if that would work is, so I'm told that this interactive learning stuff is all the rage. They must be having different kinds of students who interact during that course. Let's see. This is up. So I like these kinds of pictures because it's easy to forget one idea, but if you somehow connect one idea to many other ideas and they become a clump of ideas, hopefully your brain doesn't have such small holes. I mean, unless if your whole brain is kind of empty, then the whole thing will fall through and, you shouldn't complain. But, you're not likely to lose, wholesale an entire idea because it's connected to a whole bunch of other ideas, and so hopefully it won't all fall through. It's like, we put this thing, sieve in the kitchen sink, right? So, and if things are bigger flakes, then they won't get through. In fact, I think this is also true, talking about this for you're not old enough, but if you get to my age, you'll start worrying about cholesterol. And the small cholesterol is bad, the large cholesterol is good, because, essentially it just gets through fast. Okay, anyway, so we want to convert the small cholesterol of all these ideas into a large cholesterol where things are connected. So I suggest any of you can pick a pair and tell me how they are connected. I just wrote some words there. And it turns out that you can play this game, until cows come home, which apparently they don't in Arizona, so we'll be here for a while. But pretty much every pair, you can try a line and say they're connected somehow. So who wants to tell me something?
CSP and SAT.
CSP and SAT, good. That's not bad. So what is the connection?
It's a constraint and satisfiable, and SAT is the constraint satisfaction problem, basically. You have to satisfy some constraint to get it solved.
So what's the exact connection between SAT and CSP? What is
Boolean.
exactly? SAT is the Boolean CSP. Boolean CSP is SAT. If the variables are all Boolean, then it's SAT. Okay, draw me more lines. If not, they're all falling through. After the final, they'll be gone. And so you just wasted a semester. So you need to make them into bigger flakes. Yes, sir?
A-star search is a form of informed search.
A-star search is a form of informed search. Fine. Okay. Yeah, if you don't speak up, all the easy ones will be gone. And then you'll be really stuck with the hard ones.
Adversarial search and alpha beta.
Adversarial search, yeah, okay. By the way, these points will be fewer. These are all, I'm thinking of, obviously, participation credit, right? So, adversarial search, alpha beta pruning, so exactly what is the connection? The second order connections, I will be much more impressed. Yes, go ahead. It's like we talked about them at the same time, is what you're saying. Right?
It's a form of adversary.
Okay, so here is a dare. Draw a line between alpha beta pruning and A-star search. No. Heuristic as in the English word heuristic, where anything is heuristic. Right. Draw a line between, what I'm saying is draw a line between alpha beta pruning and A-star search.
In both we use the heuristic, but alpha beta pruning will prune the.
No. I think A-star search actually prunes. Do you realize that A-star search prunes, by the way? You guys were very impressed, so I had to temper that impression, that over enthusiasm for alpha beta pruning. Everybody was so impressed that, man, alpha beta pruning prunes. If we did not learn anything that prunes, then we won't be here. Everything prunes. Alpha beta pruning is actually, it uses 2 bounds. I would argue that A-star search prunes using 1 bound. Think about the following question. When A-star search is done, is it the case that all branches have been completely taken to the terminal nodes? How do you know that those branches suddenly won't become better solutions?
You go by F measure.
What?
If F measure goes low.
Yeah, but so what is the point there? The point is, basically, if I have a bird in hand, it's worth more than 2 in the bush. Right? If I have a complete solution which is 15 units costly, and I have a partial solution that is 15 units costly, I don't need to go worry about that partial solution. God forbid if it is 15.7 units costly, I would certainly not worry about it. But even if it's 15 units costly, I won't worry about it. But that's sort of like what alpha beta pruning was doing too. Do you guys see what I'm saying? Okay, A star search gets done without ever. So in fact, it's a question to ask. Does A star search look at the entire search tree before finding the optimal solution?
No.
Why were you so impressed at alpha beta pruning? Because it finds the optimal move without looking at the entire game tree. What did A star search do wrong other than coming at the beginning of the semester? Right? It did this too. It did this with 1 bound. You understand what I'm saying? And this, by the way, so A star search, so that idea is called branch and bound. It's a general idea called branch and bound. Okay? Branch and bound. So you branch, you got a complete solution which is 10 units long. So any partial solutions which are 10 or greater than 10 can be killed, even if this is not yet the optimal solution. Do you see what I'm saying? And then, so the only thing that are left is, since I already have a complete solution which is as good as 10, all the partial paths which are already equal to or greater than 10 can be killed. Then a few will still be left that are like 9.7, 8.2, etc. Those still need to be expanded. And then you might find a slightly better solution. When you find that better solution, let's say that is like 9.3, you got a complete, this thing basically 8.2 went down and became a 9.3, which is a complete solution. Now I had a 10 solution, I had a 9.3 solution, which is my better solution now. 9.3. So what is the true cost of my final solution? True cost of the optimal solution? It's less than or equal to 9.3. I have a bird in my hand. It's 9.3. If you say stop, I will take 9.3. I can't do worse than that. This is what you do in branch and bound until you have no more paths left to be expanded. Then whatever is your bound becomes the solution. A star search does this all in one fell swoop by keeping that open queue. You get that, there is no way, first of all, you would not be impressed by anything. You shouldn't be over-impressed by anything. I'm so happy that people liked something, but on the other hand, I'm also unhappy that they liked it too much. Okay? Right? You shouldn't be over-impressed with anything. Alpha beta pruning is nothing but a 2-bound version of A star's branch and bound. So there's a connection there. So we should put that in red because that's a second order connection. Which is a 1-bound version. Yes, sir.
Pattern databases is related to informed search.
Yes, that's true. But that's not red though. That's kind of proximity connections. Those are just in green. You get me a red, I would be very happy for you. And given that the grades are going to come soon, if I'm very happy for you, things can be good. Okay. Informed search and pattern data. Why am I doing this red? I got a green and then I went back to red. Yeah. Yeah.
Laplacian hypothesis pattern.
Okay, tell me why.
Because if there's some hypothesis missing, then Laplace smoothing adds a virtual hypothesis so that the priors are removed.
You close to the red.
Yeah.
Just don't drop it.
I'm not able to express it rightly. But
So
if some hypotheses are missing, then it's if we are considering. I mean, it's not like if we are considering training data for 10 examples and 11th example is the example of next hypothesis, then we won't miss that hypothesis because we are adding.
So basically, Laplacian smoothing is acting as if you have seen virtual samples. The reason it saw virtual, once you sees virtual samples, it has a prior on the hypothesis. So Laplacian smoothing is sort of trying to establish a hypothesis prior. But that's a nice second order thing. Yes, Michael.
Pattern database is an adversarial search.
What?
I don't know, but sometimes you might use like a heuristic. Instead of playing a game of chess and you have full control over the center, wouldn't that be something like a pattern database heuristic?
No, I don't know of any obvious connections there. It would look like there should be, but I don't. It's not. There are not any obvious connections. Yes.
Between satisfy sat and entailment.
Sat and entailment. Yeah, that's a kind of a nice green-red connection. What is it?
In order to see if something is entailed, you have to see if there's a world in which it's satisfied. Or
No. So tell me. No. Complementary. So
Complementary,
to
yeah.
show that something is entailed, you need to show that there is no world for where the theory is
negation
satisfied.
Yeah.
Okay, so it's sort of, that's a nice connection there. And then we established in the class a nice connection between adversarial search and real-time search. Because if you consider nature to be your enemy and time to be your enemy, then essentially you went from depth-limited min-max to real-time A-star search in the last class. And that's a great connection. Essentially, a lot of ideas from game search, adversarial search, came into single-agent search. Because that's, in game search, typically you have resource limitations and so on. So those need to be taken into consideration. Yes, somebody who hasn't spoken yet. Yeah.
Inference in Bayesian and learning.
What?
Inference in Bayesian and learning.
Inference in Bayes nets and learning. So where is learning? I have learning somewhere.
Right.
Okay. So what is the connection?
Because Bayesian learning is inference.
Yes, that's a good connection, and that we did establish that in fact there is no difference between Bayesian learning and Bayesian inference in the pure Bayesian case. So actually there's a lot of learning algorithms that use Bayesian learning, and the learning there is a misnomer. They just learn how to do, they just basically figure out how to do inference. Okay? And typically those inference techniques are harder than the inference techniques we studied in the class, because to get the hypothesis to be, remember that when you do Bayesian, true Bayesian learning, hypothesis becomes a random variable. And typically hypotheses are continuous valued random variables. In this class we looked at discrete valued random variables. Those are easier to handle. If you have continuous valued random variables as part of the Bayes net, those inference techniques are essentially second order complexity. We didn't talk about them here. But they're still doing inference. It's just they're more difficult techniques, slightly difficult techniques. And then when they do that, then essentially they just keep computing the posterior on the hypothesis. They keep computing the posterior on the hypothesis, and when they run through all the examples, then whichever hypothesis seems to have the highest posterior, that's the one that's winning for now. If you ask me to pick up one, I will pick up this hypothesis. Okay? Anybody else? There are other things too. I mean, I don't want to draw on the
Maybe
inference
inference and planning.
what?
Inference and planning.
What is that connection?
So maybe the representation of your world is a stochastic one, and there for computing the actions you have.
No, inference in Bayes nets and planning can be connected. Yes, in fact, but we didn't talk about it. The idea would be that actions can be seen as what are called dynamic Bayes networks. 2 times sliced dynamic Bayes networks. We didn't talk about them in the class, but that's possible connection. Yes.
Planning graphs and planning.
Yeah. Yeah. Yeah, but I think it's probably not worth trying the green arrow on the, I mean, if it's a really good red arrow, I will try it on the ASU's wall and then make you pay for the tuition, extra tuition or something. But this is, yeah, that's a good connection, I guess. Yeah. Yes, sir.
Local search and SAT.
Local search and SAT. So what is the connection?
In some cases, local search is a very effective way to solve a SAT problem.
Yeah, but in some cases, local search is a very effective way to solve any problem. That's good too, but it is a connection, but I would want you to remember that local search is an effective way to solve lots and lots of problems. Tell me all the places where you did local search in this course. What? No. Entropy thing is a greedy search, so in some sense, it's a kind of a local search. Perceptron is clearly a local search. In fact, one of the interesting things, I hope I mentioned this in the class, when you are doing continuous optimization, systematic search is for the birds. And even they won't like it. Because you cannot just branch on all possible values of a real valued weight and try to check if each of them will get you to optimal something. Okay? In continuous search, you always do local search. For continuous search problems, you always do local search. So yes, so perceptrons is also a local search. GSAT, which is the SAT algorithm that we looked at, that's also a local search. Somebody can also draw a connection between local search. Where is local search actually? No, yeah, local search out there and entailment. So here's the interesting question. Local search is connected to SAT, SAT is connected to entailment, so local search is connected to entailment. In what way is it connected? By not being connected, basically, because you cannot use local search algorithms to do entailment. To do entailment, you need to say that there is no model for this theory. And the answer for that is I thought for a while and I couldn't find one, so there is no model. That's not an answer. You need to have, pruned all the branches and there is no, models left that can be the model of this theory. And local search always just looks for a model. And so if it didn't find, there is no way local search can show that a solution doesn't exist. Probably doesn't exist. And I mentioned, I believe, that one way local search can become more and more systematic is to remember the places where it has been. But then to be complete, it has to remember every place it has been. And that means remembering the entire search space in the end. Okay? And the beauty of systematic searches, ultimately the difference between local search and systematic search is a systematic search is a search which has these two properties. Don't leave any stone unturned. Again, these are English proverbs. Don't leave any stone unturned. That means look under every possible stone to see maybe there is a solution there. And don't turn any stone up indefinite number of times. Both are important. If you have both, then you have systematic search. For example, IDDFS is systematic because it does eventually look at every part of the search space. And it only looks at any single part of the search space a finite number of times. Whereas local search can come to the same place many, many, many times and not realize it because it doesn't remember anything. And you make it remember it by remembering some sort of a taboo list of places that you have been to that you don't want to go again. And that's basically the idea of taboo search. And as the taboo list becomes as big as the search space, then it becomes complete. Then it becomes systematic. Okay? And one of the interesting, like a high level, deeper points is to make the search systematic, you wind up constraining the way it looks at the tree. One of the things that will make sense to understand, one of the points there is consider a scenario where you're searching through a big tree and then you are right here and you this node here. This is the node I really want to get to. Unfortunately, this node, it comes from a different branch. To get here, you have to go all the way up to the common ancestor and come down. Backtrack all the way. Just because you saw something nice, it doesn't mean that you get to just give up on what you have and go to that place right away. There is a regimented way in which you get to look at the search space. Local search, on the other hand, has no commitments. I mean, imagine a scenario where basically, society, for example, has a sort of a systematic, commitments for your mates. You might have a mate, your girlfriend or boyfriend, and then you look at somebody else, they look slightly more interesting, and then, because you are not in hippie society, you don't get to say, yeah, now I'm just stuck with this, this goes away. Right? You have rules, regimentation. And so you are regimented in the way you get to search the space of your potential mates. Whereas if I'm allowing you local search, then you will be better off. You'd essentially just keep trying every possible thing which looks slightly more interesting. And then you have infinite freedom, but on the other hand, you might keep coming back to the same place many, many times. And this idea is actually a very deep idea. Systematic search reduces the freedom of the search to make it systematic. The question would be the very best systematic searches would be those that allow you the maximum amount of freedom to the search while still ensuring that they will never go back to the same place more than once. Local search already has this, but it's not systematic. Okay? And there are some ideas, I'll just throw in a name which we would not discuss here at all, called dynamic backtracking. And this is an idea where you will start putting regimentation only on a as-needed basis. There is no search tree. So dynamic backtracking is search, systematic search, without a search tree. Have you heard of a systematic search without a search tree in this class? No. Every search tree, every systematic search had a search tree. The only guys who didn't have a search tree are things like GSAT. But there are ways in which you can make systematic searches have more movement. By the way, I just remembered back in the first homework, you considered an idea called iterative broadening, where you act as if everybody has only one branch, and then everybody has two branches, then everybody has three branches. Why did we do that? And I mentioned at that time that this is most useful if the solutions are non-uniformly distributed at the leaf level. Then if you make a single mistake, you're stuck. And you will see, wow, there are all the solutions there, but I'm stuck because I have to look at this entire subtree before I get to look at them. Iterative broadening will allow you to, kind of look at big chunks of search tree at high resolutions, low resolutions at once, so that you're more likely to find the solution. So iterative broadening is something that tries to reduce the commitment inherent in the systematic search. Okay. So I would suggest you think of other connections on these. That's another way of looking for ways to not forget. And also to appreciate the ideas more, because as I said, pretty much I will be able to draw a line between anything here and anything else here. Some of them are green lines, some of them are red lines, some of them are deep red lines. I mean, they're truly deeper connections. And figuring out those connections is always very useful. Okay, so I did say that I will shift gears at 5:30. So it's 5:30. So I'm going to I think we were kind of doing a non-systematic but deep review of the course, even though you don't appreciate it. Okay, it was a little too deep, but we went on to specific directions and went deeper in those directions. So you now come up and then basically do a systematic but shallow review of the course, because it's only 15 minutes. If I can actually complete the entire course review in 15 minutes, why did we waste 4 months? Right? I am from south of India and I can speak very fast, but not that fast. Okay. So we saw this picture in the beginning. In fact, I did mention that when we looked at this particular discussion, I mentioned that these are series of lectures that would make a lot of sense after the course is over, but I have to do it in the beginning. And in the past, I didn't have a way of making you remember what I did in the beginning. Now we do. There's a YouTube video waiting for you if only you want. Okay, you can actually go back and listen to the second and third lectures, I think, and they are about the overview of the AI that we did in this semester. And they make a lot more sense now that you know some of the details. Okay, so it's worth listening to again. But anyway, so we looked at this intelligent agent design architecture, and then we said we need to figure out how to represent the knowledge, how to write that knowledge. Either you acquire it by humans write it in, or you learn it. Okay. And if you do have the knowledge, then how do you answer the question of what do I do next? Every agent we have looked at is trying to decide what to do next. The game agent was trying to decide what's my next move. The single agent was deciding what's my next move. Stochastic agent was deciding what's my next move. Okay. So, and then we talked about the fact that, that I said that we will look at least two kinds of representation, logical and probabilistic representations. We did that. We talked about a variety of inference. There is atomic inference, which is basically blind and informed search on atomic states. Okay. And then we looked at factored models, where the world states are made up of essentially state variables and their valuations. Okay, and then we looked at SAT and planning are both factored models. And in both cases, we were able to come up with more interesting search algorithms, which are eventually special cases of the atomic search, except they get to exploit the structure of the factored spaces. Okay, so that's something that we said we'll do, and we did that. And the inference on the variety of representations we did for logic, we did logical resolution. For probabilistic logic, we did Bayesian inference. And in each case, it's not just one. I think resolution is like the ending of the logical inference, but sometimes you can just get by with mod exponents. And similarly, Bayesian inference, we looked at variety of cases. We looked at systematic as well as sampling-based inference techniques. Okay, so this picture still kind of tells you, what did we say we'll do, and that sort of we did those parts. Okay, so that's the connection as to why each of those pieces. When we're talking about a specific algorithm and we are in the very deep details of that algorithm, it's easy to lose track of why are we doing it. But it's still possible if you come back here to see why those are connected. Okay, so that's sort of what we were planning to do, and we did that. From the point of view of AI textbook that you used, I think this is one of the versions, the second edition, I think, the chapter numbers. I would think that we did a pretty good job of covering, all the green chapters. Didn't touch the red chapters at all. And so you know what parts we didn't do. For example, you won't be surprised when I say that we did very little about how the agent senses the environment. We just assume that the sensing has been done and the knowledge has been represented in some symbolic format. Okay, that's a huge thing that we did not do. Okay, so the sensing part we didn't do. This whole part we did. Uncertainty, handling uncertainty we did. Probabilistic reasoning over time and making simple decisions. I have come close enough that if you look at those chapters, it would still make sense. For example, probabilistic reasoning over time is what the dynamic Bayes networks would be, which is the connection to planning and probabilistic reasoning. Okay, and then some of the things that, and then we did not talk about, in learning, for example, we didn't talk about how do you use prior knowledge. In fact, we did in some ways, the algorithms which start Bayes network learning algorithms, which start with a particular configuration, a particular topology, because somebody told them that's the topology to look for. They are not only starting with examples, but they have a significant bias in terms of prior knowledge. Okay, but there are approaches for writing knowledge you have in more declarative fashion, and we could have done more of that in knowledge-based learning. But we did, the parts where we assumed somebody gave us like the entire topology, and then we used that to figure out the parameters. That is sort of using background knowledge. Okay. And then as I said, I didn't do any of this. And philosophical foundations, I didn't directly do it, although you guys did some of it on the blog, because I can't stop you from philosophizing. And AI present and future sort of was inherent in various places. But so that's how the course stacks up in terms of the chapters in the textbook, which is a hefty textbook. So we sort of had a reasonable coverage. Okay. So, and obviously people say that it doesn't matter what you cover, but what you uncover. Okay, so I, even before I covered, the textbook covered everything, and it was there. And there is this whole entire question in my mind that by starting next year, every possible course, including mine, have already been videotaped. I don't ever have to speak again. I don't have to look at students' faces. Students still have to look at my face, but they can sleep while I'm talking, and won't hurt my feelings. Okay. Everything is out there. The question is, what did you get? Of course, we can go to a point where we all have personalized robots who will do our work, and then it will be like that valley where we'll become nice and fat and we'll sit somewhere, and then somebody else does all our work. But the real question is, how much of it did you get? These are a bunch of, Far Side cartoons which talk about what we talk to people and what they get, including people which are not humans. But anyway, so I did want to get a feeling for what is it that went through. Clearly, short of lobotomizing, which I believe I'm not allowed to do, I can't quite tell what exactly went through. I can assume that the tests are some idea, give me some idea as to what went through. But many a time, you might get thinking about this later on too. One specific thing that I try to do is this interactive semester review on the blog. And I'm actually very happy that people did this, pretty seriously. Yeah, so there you go. I'll put a link to this directly from the class page. And it basically has 38 people writing. I think it's not 38. Some of them are removed, but I think we have about 36 students, and they all wrote, I believe, as to what they got out of the course at a certain level. Okay, and I would certainly suggest that you look into it. I did. I looked into every one of them, including the last one that was just sent after I came into the class. But because I had to put this up. But I think it's a good understanding of what it is that people actually got out of the course. And that makes more sense than me reviewing it, because you reviewed it yourself. This is the word cloud of as of 2 o'clock. If you take all the comments and throw it into the Wordle, this is the word cloud. In fact, there are all sorts of nice word clouds. Whichever you like, you can take it. This was one. That's another. Okay. So you can clearly see, a lot of people like search, heuristics, Bayes, came up, game came up, game trees came up, alphabet of pruning came up, planning graphs came up, a lot of things came up in, the comments that people made as to what they got, and that's pretty good. Here are other things. You can send this to your parents saying your tuition dollars at work. This is all the concepts I learned, and they'll say, well, who did you help? Well, that's a different story. So, many of the comments, some of the comments at least, were sort of fairly recursive in nature, saying, I appreciated planning graphs because they taught me about planning graphs, which turns out you can say that about any X. I appreciated X because it taught me about X. But there are also, a fair number of comments which, I thought went into more deeper connections. Just as I was reading through, some that struck my attention, I just, put them here. I'm just going to quickly go through. I'm not going to read them, but, you can, the slides are up, so you can go look at them later on. And I would actually suggest that you look at all of them anyway. So this is one which had, I thought, second order connections. That's another that had some interesting second order connections. That's one more that had second order connections. That's one more. That's one more. I may have missed some of them, but those are the various ones, which sort of made me feel that I wasn't just talking to the walls. Some things did get through. Okay. Unfortunately, I think in a course like this, the tests will only test a certain level. There's a lot more that you can get. It's not just because me standing here. There's just, it's a rich number of connections between concepts. And I was really hoping that you'll get a lot more than what I can test in the tests. And I think, some of you actually did manage to do that. So I'm pretty happy with that. So then the last but one slide is, what happened with this? There's something wrong with this slide. Yeah, anyway, okay. Well, this doesn't work here, but I can't help it. So this is my usual slide. Am I even in, oh no wonder. Yeah, that's the way to do that. How many of you have seen Schindler's List? Okay, and so this is my Schindler's List routine. Right, so obviously I did the slideshow. Okay, so those of you who saw Schindler's List, you know that there is the ending of Schindler's List where Schindler was really, really unhappy that he didn't do more, didn't give away more gold. And obviously, now that the semester has come to an end, I too have this feeling that I could have given away more pearls of wisdom to you. Opinion might differ on that. But I am going to try and tell you some of the things that I would have spent more time on if I had more time. So one thing, as I mentioned, is perception, which is certainly something that I should have spent a lot more time on in the class. And I think we don't have, I'd say really should be a two-part course. In the learning parts, we could have done more about things like reinforcement learning, where you get partial, information about the label, not full or no label. Okay, so we could have talked probably more about reinforcement learning. And another interesting point, which is actually a deep idea, which I didn't get a chance to look at, is if you learned, given a set of examples, if you learned a decision tree, okay, and it captures most of the examples but doesn't capture some of them, then can you improve the decision tree you learned? Using, okay, we should stop this. Otherwise we'll outcry now. Can we improve the decision tree we learned? Can we improve the decision tree we learned? So can we so one of the things you do when you prepare for exams is you first learn some of the concepts, then you see that some of the problems you didn't get it quite well, so you spend more time on that. So the second learning would be focused on the parts that didn't go well in the first learning. There are ideas in machine learning called bagging and boosting that actually do this. That's a beautiful topic to discuss. One other idea that I would have liked to talk about, and that sort of becomes the first topic of the next course I'll be teaching, I think, 571 Graduate Level AI, is Markov decision processes, which essentially talk about the point that in most real-world domains, there is no single goal state. There's no goal. The people tell you that it's journey that matters. So you get through the journey, collecting rewards on the way, and then what are you optimizing in that case? And that would be the Markov decision process model, and it's a beautiful model, and it's an atomic model which we didn't talk about. And we should, we get to. I think in chapter 17 in the textbook, the endings are discussed. I would have spent much more time, I guess. If we have more time, we should think about multi-agent topics, multi-agent X. The closest we came to multi-agent is alpha beta pruning and game research. There's a lot more that's going on there. Okay. And then, as I said, I should have done first order logic if for nothing else but that when Chitta Baral finds out that I did a 471 and didn't actually teach first order logic, he'll be after me with a pitchfork. And so, just please read up, first order logic chapters when you go after me. Okay. So that's my stick on the Schindler's List. So there is a statement that I really like about Marvin Minsky, who, as I said, is one of the founding parents of AI, and he said, "With understanding comes a sense of loss." Okay, my hope was that you got a sense of loss, not just a loss of a semester that was gone before you realized, but a loss of some of the magic, because you can't implement magic. Okay, you implement techniques. And I hope you understand how some of the intelligent agency works, and some of that magic is lost, and so that's your loss, and I hope that you did experience some sense of loss. That's all I wanted to say. Thanks for suffering through the semester. For those of you who actually went through the entire semester, brave souls, and I'll send you the exams soon enough. Okay, thank you.